Section 7.4, Inverse Laplace Transforms, Part 2. So in this section, we just continue our partial fraction decomposition from last time. This time we're looking at case 3, which is the case where we have irreducible quadratic factors in the denominator. So as a concrete example, let's look at 2s squared plus 10s over s squared minus 2s plus 5 times s plus 1. Remember that this is a distinct linear factor. It's not repeated. This is a distinct linear factor. And this is an irreducible quadratic, which means it does not factor over the reals. One way you can be sure that a quadratic is irreducible is that its discriminant b squared minus 4ac must be negative. So if you're not sure, you can always check that. Now, if you may remember from the general partial fraction theory, when you have an irreducible quadratic, what the theory says is that you should get a term that has that irreducible quadratic in the denominator, and then in the numerator you should get a general linear function. So this must be an as plus b, not just an as or just a b, but an as plus b. When you have an irreducible quadratic in the denominator that's not repeated, you should just get a general linear function in the numerator. And now, just like before, if this is a distinct linear factor in the denominator, then you should have a general constant in the numerator. So this is exactly what you did, say, before in calculus or algebra when you did partial fraction decompositions, and this is absolutely correct. However, we're going to tweak this just a little bit. We're going to stay consistent with the theory, and we want to use an algebraically equivalent form for this, for what we have up here, so that not only will it be correct in the terms of the theory of partial fraction decompositions, but it will be easier to use in terms of inverse Laplace transforming things based on a table. So here's what I mean by that. Let's begin by taking our irreducible quadratic and let's complete the square, because when we go to do inverse Laplace transforms, we don't see anything like this, denominators like this in our table. So what we want to do is complete the square, and if you remember how to do this, we just rewrite this as s squared minus 2s plus some number that completes the square. And so I'm going to, the number that completes the square here is we take the coefficient of the s term, we half it, and then we take the result and we square it. So the number that completes the square is a 1 here. So if I add a 1 here, to keep things even, I need to subtract the 1 back off. And now this will always factor as a perfect square trinomial as s minus s, this sign, and the square root of this number. And so here we have an s minus a 1 quantity squared, and then this is a 4. So we'll rewrite this as a 2 squared. And now I will take this irreducible quadratic and write it as a sum of squares. This is going to make it very table friendly in terms of inverse Laplace transforms. So we'll just take this, we'll rewrite it like this. Notice that these are algebraically equivalent. And now we're going to do something that might feel a little bit more strange. And remember, what we're going to do is we're going to take our numerator, our yet to be determined as plus b in the numerator here, and we're going to look for something of the form d times s minus 1 plus 2 times e. I'm going to use different letters. I'm thinking that we've already burned the letters a and b. We've used the letter c. I want to generate a new form for this, and I'm going to use d times s minus 1 plus 2 times e. And what's the idea here? Well, notice this is still consistent with our partial fraction theory because this is a general linear function. If you were to multiply this out, you get a ds minus d plus 2e. So that just looks like a constant times s plus another constant. This is just maybe an overly fancy way to write it, but this is the way that's going to make our life easier in terms of inverse Laplace transforms, and you'll see why in just a few minutes. So the idea is, how did I know to take this form? What I want to do is a constant times this shift, this s minus 1, plus whatever the number is here times my other constant. So I want my shifts to match, and I want what we call the b in our table to match. And this is going to make our life a lot easier when we go to do inverse Laplace transforms. It's still consistent with the partial fraction theory, but just has a slightly different form that is more table friendly. Well, now if we have this form for the decomposition, we need to find the constants d, e, and c, and this plays out just like we did before. So we really have this equals this. I'll multiply through by the common denominator. When I do, on the left-hand side, I get this stuff. When I multiply this term by the common denominator, remember this and this are the same things. So I just get d times s minus 1 plus 2e all times s plus 1. Let's show that. On the left-hand side, I just get what was in the numerator. On the right-hand side, I get this times s plus 1, the brackets are very important here, plus c times my irreducible quadratic, but written in this improved form. Now we can just use the cover-up method. I'll go through this quickly. We've done this many times. A judicious choice here maybe is to take s to be minus 1 because it covers up this term. And if you do that, you get c as minus 1. Another judicious choice is maybe to pick s to be 1. If you do that, you get this equation where you have one equation and two unknowns, but we already know what c is, so we very quickly get e is 4. And then lastly, we need to make a third choice. We have 3 constants, so we know we're going to have to make 3 choices. I'll just pick, say, s to be 0, and if I do, this very quickly leads to d being 3. So where are we going with all of this? That says the original rational function that we started with had this template as its partial fraction decomposition. And after we did the algebra, we saw that the d was 3, the e was 4, and the c was minus 1. And I want you to leave it in this form. You're going to see why we don't want to multiply this out or do anything else. Leave it exactly in this form. It's going to be the most table friendly. So how does this help us to calculate inverse Laplace transforms? Well, here's how. If this is equal to this, then the inverse Laplace transform of this is equal to the inverse Laplace transform of this. That's what I've written here. And now by the linearity of the inverse Laplace transform, I can break up the inverse Laplace transform over this addition. And now, using algebra, I can split this fraction as 3 times s minus 1 all over this, plus 2 times 4 all over this. And that means I can split the inverse Laplace transform up. So I'll split the inverse Laplace transform up one more time into the 2 pieces that are here, keeping the common denominator. And now let's analyze this. When you look at this, maybe we'll start with the easiest one here. This, we can pull the minus out by linearity. This is something that's familiar to us. It's in our table. If we just read our table backwards, this inverse Laplace transforms back to e to the minus t. We still have the minus. If we look at this one, well now, if we remember our shifts have to match, this is a shift in the s domain, so that corresponds, and it's a shift of 1, so my shift is 1. So that means if we were just to cover up the shift, that we know the shift of 1 in the s domain corresponds to multiplication by an e to the t in the t domain. So if we cover this up and we view this without the shift, this looks like something that inverse transforms back to sine 2t. It's crucial. Now notice I pulled the 4 out. I left the 2 because in order to use our table, now you'll see why I was doing what I did, these b's have to match. So I had to keep the 2 here. I don't want to pull all of this out. Otherwise, it doesn't match my table. And so I pull the 4 out. Here the shifts match. I have a shift. The b's match. And this inverse transforms back to an e to the t sine 2t. We still have the 4. And last, we'll keep this going here. I notice here the shifts match in s. Whenever I have an s, the shifts have to match. The a is a 1 here. If we cover up that shift, that looks to me like something that inverse transforms back to a cosine 2t. So notice my b here is 2. And so this inverse transforms back to a shifted version of a cosine 2t. And what happens in the t domain when you shift in the s domain is you multiply by an exponential. So this is an e to the t times a cosine 2t. Don't forget the 3 that's out front. So we pulled the 3 out here. Here we pulled the 4 out. We left the 2 knowing that our b's had to match. We'll deal with our shifts. Our shifts had to match. Now you can see why we use this form right here. Looking ahead, the reason, let me scroll to here, the reason that this form, if you're looking down the road at inverse Laplace transforms, the reason that this form right here is an improvement on this form is that the shifts already match. And the reason that this form is an improvement on this form is that the little b's already match. So we're making things match from the outset. It's not going to cost us any more work. We still got to find the coefficients. And we just have things ready-made so that when we arrive at this step, we have matching shifts. We pull the 3 out. We have matching b's. We pull the 4 out. This had nothing to do with any of that. So we just invert this like we always do. And we're able to take this quite complicated function and inverse Laplace transform it very quickly. So the key concept here is we want to handle irreducible quadratics in a way that's not just correct according to partial fraction theory, but it's correct according to partial fraction theory and helpful for computing inverse Laplace transforms. So this will take a little bit of getting used to compared to what you did, say, in Calculus 2 with partial fractions, but it's just a minor tweak of what you had done there. Let's look at another example. So suppose you had the inverse Laplace transform of s minus 4 over s squared plus 2s plus 3. So if we look at this, we see, if you can check, that this is an irreducible quadratic. And so if we complete the square to make it look like a sum of squares, then we write this as s squared plus 2s plus the magic number that completes the square, plus 3, and then we have to subtract off the number that completes the square. So we take the 2, we half it, we get 1, we take the 1 and we square it, we get 1. So the number that completes the square is we put a 1 here and a 1 here. So then refactoring this is an s plus 1 quantity squared. This is a 3 minus 1, which we write as 2, but we have to write it as a difference of squares, a sum of squares. So we get s plus 1 quantity squared plus, we'll write this as the square root of 2 squared. So that means when we have this, we're going to rewrite this. We know our new denominator is going to be this. These are algebraically equivalent. This is the preferred table form. And now what the theory says is if you have an irreducible quadratic in your denominator, then you should have a general linear function in the numerator. And we'll do that, but we'll do it in a table-friendly way where our shifts match and our little b's match. And so we have an a times s plus 1 plus a b times the square root of 2. We'll find the coefficients using our standard technique. We'll multiply through by the common denominator. We get an s minus 4. Over here we get an a times s plus 1 plus b square root of 2. We'll make the choice of s equals minus 1. We'll find b. We'll make the choice of s equals 0. We'll find a. And so that says that this original rational function can be rewritten in this much more table-friendly form like this. And now we're ready to inverse Laplace transform the pieces. Notice everything is ready-made to inverse Laplace transform. Here, this looks very complicated, but we don't panic. What we want to do is split this. We want to split this to where all of this is in one term, all of this, and then all of this is in the other term. So we're just splitting the two pieces that are right here while keeping the common denominator. Now notice the shifts already match. We can pull the 1 out or not, it doesn't make any difference. The shifts already match. I see that my b is the square root of 2. So since my shifts match, I just cover up my shifts. I notice that my a is a minus 1. My b is a square root of 2. And so this looks like an e to the minus t times a cosine square root of 2 times t. I just cover up the shift. That looks like something that inverse transforms back to a cosine square root of 2 times t. And then the shift amounts to a multiplication by e to the minus t in this case, because my a is minus 1 in the t domain. Secondarily, when we have this, we have to realize which one of these constants do we want to pull out. Well, we always know we need our b's to match, so we want to leave the square root of 2. We'll pull this constant out. And now our b's match. We see that our shift is a minus 1. If we cover up our shift, this looks like something that inverse transforms back to a sine square root of 2 times t. And then the shift of minus 1 amounts to multiplying by an e to the minus t. And so we still have our minus 5 over square root of 2, e to the minus t, sine square root of 2 times t. So try these in the homework. Practice doing your case 3 with your irreducible quadratics. Try this new look in the numerators so that they are table friendly and see how it goes for you.